All right. Awesome. Well, good morning and welcome to Ohio Stormwater Association's webinar, Engineering for Climate Change, presented by Daniel Christian from Tetra Tech. My name is Dana Heineman. I am a member of the Ohio Stormwater Association Board and the Marketing Committee, and I will be moderating today's webinar. Ohio Stormwater Association is a non-profit, non-political organization that is dedicated to the advancing of management of stormwater and related natural resources through education, leadership, watershed-based coordination, and technical assistance in Ohio. OSWA's board of directors include Kelly Commander as our president, Regina Collins as our vice president, Teresa McGeady as our secretary, Bob Lenz as treasurer, and Mark McCabe as past president. You can also see the rest of the OSWA board listed underneath board members. Water Management Association of Ohio, or WAMO, is OSWA's parent organization. So in order to join Ohio Stormwater Association, you must be a member of WAMO first. Then you can select Ohio Stormwater Association as your division. Some benefits of joining OSWA include free quarterly stormwater webinars, like the one we're on today, discounted registration at the annual MS4 boot camp training in May, discounted registration to the annual watershed workshop presented in collaboration with Ohio Water Environmental Association, and discounts on online training provided by Stormwater University, National Stormwater Center, and American Stormwater Institute. For more information about OSWA membership benefits, you can visit our webpage at ohioswa.com and then under Get Involved tab, and you can select Become a Member. Another great way to get involved with Ohio Stormwater Association is by joining a committee. So we do have 6 committees: education, marketing and membership, which I'm a part of, regulatory, transportation, industrial, and extreme weather. You do not need to be a member of OSWA to join a committee. Obviously, it is highly encouraged as some of the benefits we mentioned before. But again, you can find additional webpage for that information on that on our webpage. If you are in need of CEUs and PDHs today, this webinar is being recorded, but you do need to pay attention to get that CEU and PDH. So Dana will be sending out a link to the attendance. We will be asking a few questions throughout the presentation, so make sure you're responding to those. Don't worry, we're not going to quiz you too hard, but you do need to perform that attendance verification in order to get your CEU and PDH. All right, on to the fun stuff. So today's speaker is Dan Christian from Tetra Tech. So, Dan is a senior project manager and water resource engineer for Tetra Tech and brings over 32 years of experience in a wide variety of integrated stormwater management and resource projects. He has worked extensively with climate change adaptations for changing rainfalls and managing the risk of urban flooding. If you do have questions, please ask them in the chat. We will have some time for Q&A at the end, but with that, I will turn it over to Dan.
Thanks, Dana. Let's get my screen up here. Can you see my screen now?
Yes, we can.
Awesome, thank you. And thank you for inviting me to speak today. It's an honor to be here. I will provide a PDF copy of this presentation, and then I also have a 2-page summary of a lot of websites that I'm using, and you'll see that throughout the presentation. So don't feel like you have to write them down or do screen captures. We'll share all of that information with you so you can take a peek at all this really interesting data. So let's get started. This is a topic that I'm very passionate about. So anytime you want to talk about rainfall, just give me a call. And so here's the problem that we're faced with. Rainfall patterns are changing, but how much and where? So that's the first question that we're going to look at. Now we can look at rainfall patterns on a number of different scales. We can look at a regional scale of information. And for a regional scale, we can pull up the Great Lakes Integrated Sciences and Assessment, or GLESA, it's a website. They are a team of individuals that really focus on the Great Lakes and Midwest area, including the state of Ohio. And here's what GLESA has to say about changing rainfall and precipitation. And based on the observations of the past, they say that increase in extreme precipitation is one of the clearest changes in climate observed in the region. And in the Midwest, they talk about the most intense precipitation events have become even stronger and more frequent. And then they have lots of these graphs and tables that you can look at as well. They go on to say, and some of the, one of the pieces of information they focus on is the heavy precipitation. So this is information looking at the heaviest 1% daily rainfall events, and it's a comparison of 30 years between 1950 and 80 and the 30-year period from 81 to 2010. What they say for the top 1% events is the change in intensity has gone up by a little over 5%. The change in the number of days has increased by about 23.5%. And the change in the amount of rain coming down in those top 1% storms has increased by 24.5%. So big storms getting bigger. They go on to talk about the 2-day precipitation events. And if you just look at the graph on the right-hand side, you can see a clear trend on the number of 2-day events exceeding a 5-year recurrence interval. There's a clear trend, upward trend, from about 1960 to present. So again, big storm events getting bigger. So now, here's what GLESA has to say about the future. They go on to say that the amount of rain falling in that most intense 1% is expected to increase by another 40% by late century. The frequency of the storm events is also projected to rise by mid and late sentence, with the greatest change occurring in the springtime. The number of days exceeding 1 inch of rainfall is projected to increase by 15%, and the number of days exceeding 2 inches is expected to increase at an even faster rate, 37 to 46% on average across the region. Now, that's at a regional scale. We can also look at this on a state scale. So for the state information, we can go to NOAA National Center for Environmental Information, and they have these really nice summaries for each state. So we can pull up the data for Ohio, and what they have to say is that temperatures have risen by almost 1.5 degrees Fahrenheit since the beginning of the 20th century, and the warming is more concentrated in the winter and springtime. And if you look at the graph on the upper right-hand corner, you can see the temperature change is projected to continue to increase throughout the end of this century. Now, why are we talking about temperature? We're supposed to be talking about rainfall. So this is an important point. It's important to understand the relationship between the average annual temperatures and the rainfall. The higher temperatures lead to an increased evaporation and surface drying. And the warmer air, just based on the laws of thermodynamics, the warmer air has the capacity to hold more water. So, for every 1 degree Fahrenheit temperature rise, the atmosphere can hold about 4% more moisture. If you have more moisture in the air, then you have the ability to generate more intense precipitation events. Quite frankly, the climate scientists I talk to are much more comfortable talking about changes in temperature than they are in rainfall, but there is a correlation between the two. So back to the state information and rainfall. What NOAA has to say is Ohio has experienced significant increase in the number of 2-inch events since the mid-1990s. Now, we can also look at this at a county scale. So to look at a county or a city scale, you can go to the Climate Explorer. and you can type in your city or county. And then you're faced with this whole bunch of different tools and information that you can click on. You can pull up different climate maps and graphs. You can look at historical data and different thresholds. And what's really fun about this is you can adjust with slider bars or numbers. You can set different thresholds. I want to see the historical data for rainfalls over an inch. I want to see it, for rainfalls over 1.5 inches. Whatever it is, it's very quick and easy to play with and see those trends. So in our industry, we use rainfall data for, and I'm going to pause here. I think Dana has a question for us.
I do. That is a great question in and of itself. So what do you use rainfall data for? So please go in and check the portal that other Dana has placed in the chat. So go click that, sign in, and then the question is, where do you use rainfall data?
And Dana, should I pause for a minute or should we just keep going?
You can keep going. If anyone needs that repeated, please just type it in the chat and I will actually put it in there right now. So please keep going, Dan.
Okay. So, chances are I don't need to tell you what you use rainfall data for. If you're part of the Stormwater Association, chances are you use rainfall data for lots of different things. Here's some of the things that I use rainfall data for. Site development, municipal collection systems, the road system, drainage, depressed freeways, our natural water courses with bridges and culverts and floodplains, water quality treatment standards, just a plethora of information that we rely on and use rainfall data. So by and large, most people look to NOAA Atlas 14 as the latest and greatest rainfall statistics. I'm sure you're probably all familiar with this. You can pull up the website, you can put your little red crosshair wherever you want, you can zoom in, and when you put the crosshair there, then this table of information that's shown on the right will pop up below the map on the website. And this has a wealth of information. It has rainfall data for recurrence intervals from 1 to 1,000 years and durations from 5 minutes to 60 days. And we can generate this information at any location very, very quickly. So it's really good information. It's all based on the historical rainfall data collected over the last, really since the late 1800s. But Atlas 14 has some limitations. Historically, it's only been updated at the request of and funded by the users. So this approach has led to irregular update cycles. It's not current. The last time the Atlas was updated in Ohio was 2006. So that means we're 17 years out of date. Because of the way it's being updated, we end up with discontinuities of data at the borders between adjacent volumes. And one of the biggest problems with Atlas 14 is this assumption of stationarity. So NOAA in their statistics assumes stationary climate. So that means that all the rainfall data collected at any point, so the data from the late 1800s all the way through to the early 2000s is all treated exactly the same. And that has the effect of pulling down the average numbers in the statistics because we know that the rainfall is increasing over time and that assumption of stationary is false. And NOAA has an assessment report of that information. So the good news is Atlas 15 is on its way, in case you haven't heard. And this is all on NOAA's website. But NOAA received direct funding from the Bipartisan Infrastructure Investment and Jobs Act to do Atlas 15. And this is an update to Atlas 14. Atlas 15 will be divided into two different volumes. Volume 1 is going to focus on that historical rainfall statistical information and observed trends. And they are going to account for non-stationarity. So, and that'll be a huge improvement on the rainfall statistics. Volume 2 is then going to incorporate climate projections for the future. And they're actually going to go out to about the year 2120 on their rainfall estimates for the future. And this information will provide continuous spatial coverage across the entire US. Now, their schedule for Atlas 15 is to do a pilot of the information, and this pilot will be focused in the state of Montana, and it will be completed in next year, in 2024. We're expecting to see the continental US Atlas 15 come out in 2026. And then NOAA will pick up Hawaii, Alaska, and the territories in an atlas in 2027. At least this is their game plan. And also really good news, the Floods Act was signed into law back in December, and this fundamentally provides NOAA a requirement to keep the precipitation frequency estimates updated at least every 10 years. So, and that's going to be really helpful going forward in the future. Okay, so where can we get detailed future rainfall data from now? Because, you know, what we need right now as stormwater engineers, I need to know the rainfall depths and intensities for recurrence intervals from, say, a 1 to 200 year. I need, you know, 5-minute to 24-hour data. If you're doing a rational method calculation, you might have a time of concentration of 10, 15, 20 minutes. You need to know what the rainfall is for that time of concentration. And yet what we have right now from the regional and state summaries is we just have these general statements of trends from climate scientists and this promise that we're going to have a update to Atlas 14. But what do we do in the meantime? So there's actually, it turns out to be quite a few sources of data. So what you have here on the screen are two lists, one on the left, one on the right. And again, for those joining a little bit later on, I will provide a copy of this presentation as well as a 2-page summary that has all of these website addresses provided as hyperlinks. So you can spend an afternoon drinking coffee, surfing the web, learning about rainfall. But the list on the right are just interesting sites I encourage you to go look at. The one on the left I'm going to talk about in just a little bit more detail. So the first one I want to talk about is some really nice information out in the Chesapeake Bay in Virginia. You can pull up this website and you can put your cursor on pick a location, and you can generate these updated graphs and tables of information of future rainfall projections for different greenhouse gas and emission standards and different time frames. Really good information, but it has nothing to do with the state of Ohio. So why am I talking about this? I'm talking about this because I think this is what you're going to see with Atlas 15. This is the type of information we can expect to see in the future across the entire US. Another option is you can hire universities or consulting firms to do detailed analysis for you. We've done quite a few of these across the country for lots of different clients. I'm just pointing out one as an example. We did up in the Detroit metro area, looked at 8 different stations, lots of frequencies and durations, 6 different models. We ended up with 11,000 data points to sort through. All of this is up on the website, which is URLs at the bottom if you're interested. We summarized all that information into tables and graphs that are pretty easy to understand. And the approach that we use to do it is all documented in the reports in case you're interested. But I'm not here to sell Tetra Tech. There's actually a lot cheaper and quicker approaches to generate some very similar information. The first one I'll mention is EPA Create. So this is a really fun website. You can go, it's intended to help water sector utilities in assessing climate risk. It has these different modules. One of the modules is climate awareness. And if you can see on the screen, you can generate these maps of information. And then, for example, under storms, we have, we can look up information for a couple of different future conditions and see what the rainfall intensity is. Frankly, from my standpoint and what I do for a living, I find it more useful to kind of go behind the scenes and go to this other website and access some of the data directly instead of running through these scenarios. And the table here on the right shows an example of the type of data that you can pull up. And this example happens to be for Columbus, Ohio. And there's also, it goes through and explains how they did their analysis. They looked at 38 different climate models. They looked at CMIP5 and the greenhouse gas emission 8.5. They have the storm intensities, 5-year to 100-year. They looked at 2 different time frames, and then they grouped the rainfall from these 38 different climate models. They created 2 groups. A non-stormy group, which is an average of the 5 models with the lowest projections, and a stormy group, which is the average of 5 models with the highest projections for the analysis. So if we look at the example for Columbus, and we say a 10-year, 24-hour storm event looking out to 2060, the non-stormy, the low end range, they're projecting about an 8% increase in the rainfall. In the stormy scenario, those top 5 average models is about 19, almost 20% increase. So really quick and easy data you get to, you just go to this website, type in your address and hit the search button, and you'll be popped up this information. Another website that has even more information, because the EPA Create, if you look at it, it really is limiting you to just a few rainfall recurrence intervals. And I've personally used the 25-year storm event a bunch, and that's not one of the options. And it only has data projected out for the year 2035 and 2060. But if you go to this CERDIP website, which this was an effort from North Carolina Institute of Climate Studies and NOAA. It was funded by the Department of Defense, the Strategic Environmental Research and Development Program, or CERDIP. They created these future IDF curves for 2 different greenhouse gas emissions. Now, I will say that they have a big disclaimer on their website. The results are for research use only, so you have to take it for what it is. But what I like about this is it's so easy to use. You can go to this website, you give it a location of where you're interested in, you select what year you're interested in and the scenario, and hit the update button, and you immediately get this table that you see on the bottom with all of your precipitation information. And they made it really easy. There's a little button to download the table of information, so you can then throw it into Excel. Now, one of the problems I have with the CERDIP is it doesn't have the sub-hourly rainfall data. So again, if you're looking at something like a rational method calculation, you'll have to maybe extrapolate your own data if that's what you're interested in. So if you put together the EPA Create and the CERDIP information, you can generate information like what you see here. And honestly, this takes me longer to play with it and make it look pretty in Excel than it does to download the information. What we have is on the left-hand side is Atlas 14. All of the information shown in blue is the 10-year storm event. The kind of the reddish color is the 100-year storm event. We have the big heavy line is that median projection. The solid lines are the greenhouse gas emission 8.5, whereas the dashed line is the RCP 4.5. And then the 2 boundaries are the range of projections. So what we see here in this example for Columbus is Atlas 14 says we're at 5.63 inches of rainfall for a 100-year 24-hour storm event. And that was back in 2006. Today, we're getting pretty close to 6.2 inches. And by 2085, we're up to about 7.4 inches of rainfall with a range from about 6 to 9.6 inches. So again, very, very quick and easy to pull this information and create a summary like this. Now, here's another option for you. Federal Highways has an interesting little tool as well. One of the downsides to the EPA Create and the CERTIP information is you can't pick which climate models are of interest. So Federal Highways tool allows you to pick which climate model you want to use, which is both good because it gives you more control, and it's bad because now you have to pick which climate models, and there's like 34 to choose from. But if you're interested in this, the way it works is you go first to the Bureau of Reclamation's website and you download the climate model information that you're interested in. Takes a couple of days to get the data back. And then you take a great big ugly file that you get from Bureau of Reclamation and you upload that to Federal Highway's CMIP tool. It may take a day or two to process the information, and then they give back to you basically your IDF table. So it's pretty straightforward. And the best part is, since there are a few little nuances to it, there's a YouTube instructional video on how to go through the information, and it kind of walks you through step by step. So check that out if you're interested in looking at specific climate models. So what do? We'll pause here. Dana's got another question for us.
Yes, I do. The question is, what version of the NOAA Atlas are we about to be on? Actually making you think. So again, type that in the link in the chat. We will type the question again, but Dan, keep on moving.
Okay. So we've talked about the climate's going up. We've talked about how to get some climate data to start looking at. You don't need to spend a lot of time. You don't need to spend a lot of money. There's information and resources out there to get you started. But what do we do with this newfound information? And the best way I know how to kind of go through this is to share with you some examples of what people are doing. And then I'll wrap up with some recommendations. So first up is Lexington, Kentucky. Lexington noticed that they were designing new site plans based on the latest and greatest design storms from Atlas 14, and yet they were still having some flooding problems after the sites were developed. So what they did was very simply, they selected some historical storm events to use and incorporate as part of their design standards. A quick and easy idea to consider for your location is just utilize some of those historical storm events which have caused major problems. Another idea to think about is going back to Atlas 14. Now, this is an important point. When we look at Atlas 14, and this slide is using information from kind of the Detroit metro area, the location doesn't matter. What I want to focus on is when people pull up Atlas 14 information, they focus on a single number. So for example, in this example, a 100-year 24-hour storm event is 5¼ inches of rainfall. That when NOAA does these statistics, they apply a statistical distribution to all of the events that they classified as being a 100-year recurrence interval and a 24-hour duration. And what that 5¼ inch number represents is the most frequently occurring value, or the top of that rainfall, that distribution that they selected. There's two little numbers below that. They're usually in little tiny print, and they're usually in parentheses, and usually most everybody completely ignores them. What those little numbers are confidence intervals, 90% confidence interval. In this example, we're 90% confident that a 100-year 24-hour storm event is somewhere between 4.05 inches and 6.66 inches. Let me say that again. We're 90% confident it's somewhere between 4 and 6.7 inches. 5% of the time, the 100-year 24-hour storm event was less than 4 inches. 5% of the time, the 100-year 24-hour storm event was larger than 6.7 inches. Why do we fixate on that single number in the middle, the 5 1/4? If we want to be 95% confident that our design for a site is not going to flood for a 100-year storm event, we should be using the higher confident interval, the 6.7 inches. So think about that. Why are we focused on that middle number? Think about using the upper confidence interval instead. Now, I mentioned before the Atlas 14, one of the major problems with it is this assumption of stationarity. So the state of Illinois went through a few years back and they challenged that assumption. They said, well, what if we just, based on all the historical rainfall data, if we adjust the rainfall data to account for non-stationarity and we redid the statistics, what would we get? And that's what they did. And what they present the results in the form of these illustrations of the state kind of broken up into different areas. So if we look here in the upper left corner for the 2-year storm event, we see that 0.4 is a number written for this set of counties. So what that means is the 2-year 24-hour storm event, you need to add 0.4 inches of rainfall to whatever is published in NOAA Atlas 14. And when you look across all these illustrations, you'll notice that all of those numbers are big positive numbers. So in every case, we're increasing the amount of rainfall just to account for non-stationarity. And this is just based on historical data. And it's not trivial. If you look at a 24-hour 100-year storm event in the Chicago area, this says that we need to add 1 1/3 inches of rainfall to what's published in Atlas 14. So it's not trivial. It's a significant amount of water. Wisconsin has some really cool stuff going on. They have this whole statewide initiative on climate change, and the initiative has this working group on infrastructure led by Dr. Daniel Wright, who's at University of Wisconsin-Madison. And they have actually provided some updated rainfall information for the entire state. You can learn more about it on their website. I bring up Wisconsin not because I want to talk about the state, but I actually want to talk about the city of Madison. Now, Madison is participating in the statewide initiative, but they experienced a big rainfall event back in 2018. 11.6 inches of rain in a single day caused devastation. And they're just not willing to wait until everybody agrees upon what the future rainfall is. So they went through and they took the approach of modifying their level of service design standards. So for example, historically in Madison, Wisconsin, a site development detention basin would be designed for a 100-year storm event. Now you have to design it for a 200-year storm event. Now, Madison's not trying to achieve a 200-year level of service, but they're utilizing this as a surrogate, as an interim step until they have future rainfall data that they're comfortable with. They're making the choice to just up the level of service design standards. And they added a whole bunch of level of service. So, you know, if you're designing something along a roadway, you have to keep the 10-year storm event off the pavement. They want dry streets. The 25-year storm event, they allow some flooding, but they want that center part of the road to be dry for emergency vehicles to get through. They want, for a 100-year storm event, they want to try to keep the water within the right of way. And really what they're trying to do is keep it from flooding buildings. For the 500-year storm event, well, that's a big rainfall. They're just trying to do their best that they can to steer the water away from critical infrastructure. So that by adding all of these additional requirements, it makes a lot more work, but it provides a lot more confidence on what's going on. Virginia, and now everything I've talked about so far is just really using historical rainfall. Now let's talk about some cases using future rainfall. So Virginia Beach, Virginia went through a few years back and they said, you know what, Atlas 14 seems to be about 10% low in their area. And that's just accounting for basically the non-stationarity issue. And then they said, well, and we know that it's going to keep increasing in the future. So let's assume it's going to increase another 10%. So they just did a flat increase of 20% on all of Atlas 14's information, applied it to their table. It's easy to understand. It's easy for the engineers to utilize as they go through their design work. Boston took a little bit more complicated approach. So, and one of the critical issues to understand is this concept of designing the infrastructure to handle the useful life of that infrastructure. So if we put a pipe in the ground today, we kind of sort of expect that that pipe physically will last maybe 100 years. And so what Boston is doing is saying, well, let's look at and evaluate designing that so that at the end of that pipe's useful life, it's still meeting its level of service requirement, which fundamentally that means you then need to account for future rainfall. So they developed a whole bunch of future rainfall projections to account for that. And then they said that if you're building projects more than $10 million, you have to undergo this formal risk-based assessment. And they said critical infrastructure, and they defined what they mean by that: hospitals, emergency response facilities, et cetera. Those critical infrastructure, you need to consider this risk assessment as well. So New York City has something similar to that. They a couple of differences. One, they said, well, we're not really comfortable with this concept of the end of the useful life of the physical asset because, you know, 100 years is a long time. There's a lot of things that could happen in 100 years. So instead, they're going to use this concept of a design life. And in the case of a sewer infrastructure, they said, well, the design life is maybe 50 years. So now instead of looking out 100 years at the future rainfall, they're looking out at 50 years at the future rainfall. And I think that makes a lot of sense. They also said when it comes to critical infrastructure, it's not an all or nothing scenario. You can have critical components on most any site. So for example, if you're designing a backup generator and the concrete pad that it's sitting on, maybe that's considered critical component, and you would make sure that the pad is at an elevation high enough to consider some of these future rainfall issues. They also went through and they're currently piloting this concept of cloudbursts. And they've defined a cloudburst. You know, a cloudburst is just a really high intense rainfall event that lasts for a short period of time. And for design purposes, they're utilizing a 100-year, 1-hour storm event. And they're trying to manage the water. Now, they're not going through and saying, well, I got to design all my pipes for a 100-year, 1-hour storm event. They're trying to just more put in some storage systems to keep that cloudburst scenario from flooding the building. So providing a little bit of storage capacity and then letting it go back into the collection system when it can. So just a couple differences there with New York versus Boston. Washington, D.C., very similar approach with the critical facilities. But what they did is they said the critical facilities need to be designed based on the higher emission standards, the greenhouse gas RCP 8.5, instead of the non-critical can be designed to the low emission standards, the RCP 4.5. So yet another approach that you can look at with the critical. Australia, you know, I'll go back to a previous comment that a lot of climate scientists feel a lot more comfortable talking about temperature instead of precipitation. The entire country of Australia has this approach where they base everything on the temperature change So, and they also use a risk-based assessment and kind of the design or useful life concept. So they just look out to the end of the life of the asset based on the temperature change expected, and then plug in a formula to come up with the change in rainfall. Auckland, New Zealand took it one step further. They said, yeah, we're going to do it all on temperature. We're going to have this asset management. But then they also added a new rainfall design hyetograph to the mix. So if you're in Auckland, you have to utilize this different rainfall distribution, which I found rather intriguing. Department of Transportation, they have lots of really good resources out talking about resiliency. They, and I pulled a quote from one of their documents that I just really love. Infrastructure plan today must be able to withstand the uncertain climate condition of the future. And fundamentally, they just walk through the service life versus a level of analysis, and they look at, you know, is it less than 30 years, more than 75? And they have these different approaches that they recommend taking. So it's basically a risk-based approach. If you're interested in learning more about risk-based approach for climate, I really think ASCE has some really good documents available. They recommend basing the risk categories on use or occupancy of the buildings and structures, and recommend a climate analysis as a function of the design and life and the risk category. So good information. So just to kind of recap the different options that we've talked about, using historical storm events, using the upper confidence interval of Atlas 14, updating the statistics to account for non-stationarity. That one actually takes a lot of work. Increasing the level of service is really easy to use. Adding an additional storm like a cloudburst analysis is easy to use. And all of those approaches are done with just historical rainfall data. You know, when we look at future rainfall, you know, just using the future rainfall projections, incorporating it with the expected design or useful life, and thinking about this risk-based approach, I think are some really good ideas on how to deal with this. So some of my recommendations in general, first off, recognize that if you do nothing, if we do nothing, we are fundamentally seeing a decrease in the level of service that we're providing our local communities when it rains. The assets just have a lower level of service. I think we need to educate everyone, and I mean everyone. It starts with you and me. It needs to go to, you know, the municipalities, the decision makers, the politicians, the general public. We should have some education materials out. We should really educate everyone and do something. You know, there's a lot of questions over future rainfall projections, but, you know, do something. Don't just sit on your hands. Don't wait for things to come that are perfect, because they never will. Do something. I think you really need to understand the uncertainty associated with rainfall and account for that non-stationarity, and look at future projections. You know, start using things like the CERDIP data or EPA CREATE. Start thinking about those upper confidence intervals on your rainfall, historical rainfall statistics. And then I really think that we should be designing infrastructure to perform as intended through its design or useful life, which fundamentally that means we have to account for changing rainfall. I think we need to understand that and perform a risk and sensitivity analysis for critical infrastructure. I think critical infrastructure should be designed to a higher standard, which fundamentally means that not everything is going to be designed to the same standard. And that's a problem for some people, you know, but with the world we live in, there's financial limitations and financial resources limitations. You know, we have to be smart about how we spend money. I don't think a parking lot that serves a recreational area down by a river needs to be designed to the same standard as a hospital campus. So, you know, think about that. And I think we need to do a better job at managing those urban flooding events during the really big storm events. Too often, our standards are written so that we're only designing the pipe, to meet a 10-year storm event or something like that. And there's no consideration for what happens when the big events come. Think about having standards and think about doing an analysis to make sure that we're not flooding the buildings during those big storm events. It's okay to flood, certain areas. We can't expect to have no flooding, but we want to control where the flooding occurs. And with that, I'll say thank you.
Awesome. Thanks, Dan. We have one last question, and that question is going to be, is Ohio seeing an increase in rainfall events? I think we all know the answer to this if we were paying attention to Dan's presentation. Let me type that in. And while we have that going on, I will open it up now to Q&A. I don't see any in the chat, but if you do have any questions, again, type those and we can get those answered for you. All right, we do have one question here. Let me find all my screens again. And that question is going to be, do you have any recommendations for applying an area reduction factor to IDF curves existing or future projected at a watershed level, large drainage areas versus a smaller development site, small drainage areas? Does that change for the more intense storm events like cloudbursts? Let me know if you need to repeat that words in the chat.
Yeah, no, I think I get the gist of the question. So the area reduction factors are something that NOAA is interested in updating as well and looking at. I've heard a number of scientists say they're interested in studying that. Currently, the best information available dates all the way back from TP40 and then also the Huff and Angel work done for the state of Illinois. They have area reduction factors as well. Generally, the area reduction factors are applied to the larger watersheds to account for, the uneven rainfall that's occurring. So when you get to something like a cloudburst scenario, that's when we're talking about those great big thunder boomers that are just downpouring water in a local area. If you're looking at a site level development with that, or even a neighborhood level development with that cloudburst scenario, then you don't want to have area reduction factors. But if you're looking at what's going on in the receiving stream within my watershed, then yes, you would have to apply area reduction factors, and those big cloudbursts would logically be reduced a lot more. So you may not want to use such a cloudburst kind of concept for a watershed scale receiving stream iteration. And I have seen some studies starting to happen regarding the changing flow levels in our receiving streams. I think a fellow sent me a study from USGS that was starting to look at that as well. So, that might be something to think about at the watershed scale, is to look at some of the USGS stream impacts from climate change.
Awesome. Thanks, Dan. I don't see any other questions, but if we do have some more float through, we've got a few additional slides of information at the end, and we do want to hear from one of our sponsors, Davey. Oh, we did get one more. Okay. Do you have recommendations for applying IDF curves across a watershed, uniform to all model catchments and east to west at a certain speed, or south to north at a certain speed? So applying IDF curves to watersheds.
I think the overall IDFs, it gets back to that area reduction factors. If you're starting to talk about the east to west, north to south, that gets into some of those questions on the spatial distribution and temporal distribution of the events. And I think the best that you can do is, with today's modeling technology, you can actually simulate some of those different events. Is I would probably start by looking at some historical storm events. The worst case scenarios are when the rainfall event kind of follows the drainage system, whether it's a man-made drainage system or a natural drainage system. But when the event follows that drainage system from the upstream to the downstream, we see exasperated flooding occurring. But I don't know of any good ways, or I don't have any good recommendations on that, other than to look at some of those historical events and try those out.
Awesome. And then one last question. Do you have examples of communities applying higher design standards that reflect the upper 90% confidence interval, or accommodation for future projects of increasing, future projections of increasing storm event depths?
Yeah, so I actually was tickled when a friend and colleague said that they actually started using some of the upper 90% confidence intervals, and those were being done in the Detroit area. So that's the only example I can think of off the top of my head for that. But looking at future rainfalls, yes. I mean, if you look at the examples I went through, Virginia Beach is doing it on just a flat rate method. Boston, a lot of the climate change issues that we see are being driven first by the coastal communities because of some of the issues they're being faced with. But a lot of the larger communities on the coast, from Florida all the way up the East Coast, are starting to really incorporate a lot of the future rainfall events as well. And we see that also out on the West Coast. And then I think there's a lot of really fascinating research going on in the Texas area, but I'm not aware of what they're doing as far as designs today. But we are starting to see people incorporate this all over. And like I said, you got agencies like Federal Highways that are encouraging this. If nothing else, consider the possibilities and then make an informed decision.
Awesome. Thanks, Dan. All right, we will finish up here with the last few slides. We did want to say a thank you to our sponsors for Ohio Stormwater Association. So these are tier 1 sponsors of Butler County Stormwater District, and then our 3-tier sponsors with Contact, Strand, Davie Resource, who we'll be hearing from, and then our tier 4 with City of Dayton, Rumpke, and JEO Consulting. With that, I will turn it over to Kathleen to talk a few minutes about Davie.
Good morning, everyone. My name is Katie Mackey. I work with Davie Resource Group here in Kent, Ohio. I'm an associate consultant here. I'm also certified in erosion, sediment, and stormwater inspector through EnviroCert, and certified through the Summit County Soil and Water Conservation District for inspection and maintenance of stormwater measures in Ohio. So DRG performs stormwater management services across different industries and with a wide variety of clients. Our step one in our approach to stormwater management is always recommending and performing stormwater inspections. These inspections are performed by a qualified individual annually or weekly, or as specified in our client's stormwater agreement with permitting agencies. These inspections identify existing issues and potential problems across our clients' stormwater facilities and projects. Post-construction, there's a comprehensive report with maintenance recommendations and photos that are given to the client, as well as some maps if recommended or requested. Some maintenance items that we address regularly are vegetation management, erosion control, structural integrity, and nuisance wildlife control. We also perform long-term maintenance on these sites. Vegetation management may consist of herbicide treatments to performing biomass removals of invasive species to recommending no-mow zones. And our team of trained biologists performed erosion control with industry-tested and agency-approved materials and methods. We also facilitate, like I said, long-term maintenance items such as dredging, and perform construction earth-moving activities to bring the stormwater facilities back to compliance. So if you have any questions or need some work on some stormwater features, then we'd be happy to help.
Awesome, thank you. And then lastly, we do want to thank our affiliates. So with these affiliates, we do get some discounts for their online training. So looking at Stormwater University, American Stormwater Institute, Stormwater One, the National Stormwater Center, and NREP. So we wanted to thank you, and please check that out if you're looking for more discounted classes. If you do want to sponsor with Ohio Stormwater Association, we would love to have your support. So please contact Kelly Kubander or Bob Lentz. We offer 4 different partner levels, tier 1, 2, 3, and 4, and you can see the price associated with each of those. And then get involved with us. So as we mentioned before, we do have a couple committees: transportation, marketing, our conference committee, education, which helped put this on today, regulatory, industrial, and extreme weather. So please get involved with us. We'd be more than happy to answer any of those questions. You can email Kelly or myself directly to get involved. And then some upcoming events that we don't want you to forget about. We do have our MS4 boot camp at Kalahari on May 10th. So that is right before the conference starts. So the conference itself is May 10th through the 12th. We also have our July 12th webinar and then our October 5th regulatory update webinar. So please mark your calendars for those. And we would like to again thank Dan for presenting today. He did a great job and has been still answering some questions in the chat. So obviously reach out to him. And thank you to Dana for managing things behind the scenes. But we appreciate your support today, and feel free to reach out with us with any questions. And yes, there will be the presentation and summary sheets will be included with that, but that does conclude today's webinar.